Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video we're going to continue to talk about bolted connections and design of bolted connections and resistance of bolted connections. So far we've looked at bolted connections in general, and we've looked at the geometry and spacing requirements for bolted connections. Then we looked at yielding, which is the first bolted connection failure mode, this one right here. Now we're going to start talking about the parallel to grain non-ductile failure modes, and we're going to start by talking about row shear, which is the second one here. And we're going to talk about each one of these in turn. Okay, so what is row shear? Here's what row shear failure mode looks like. So basically what we have here is a piece of wood, and we have a bolt in the piece of wood, multiple bolts in the piece of wood. And basically what's happening is this bolt is connected to something else behind. I'm only showing one side of the connection here. So the bolt is attached to something else behind. Maybe it's attached to a steel plate or something. Let's consider that that plate is not moving. And then when we move this piece of wood up, the bolt wants to go in the other direction. So I'm pulling on the piece of wood, applying a tension force. In this case that I've drawn right here, a tension force, which means that the bolt wants to move down through the piece of wood. So what are the ways that the bolt can move down through the piece of wood? I mean, we could have a yielding embedment failure. So I could just be crushing basically the fibers around this piece of wood, and then this nail could be bending to permit that movement. That's failure mode A, which we just talked about. Another way is that since basically I have a bunch of weak shear planes running in the parallel to grain direction because I have all the fibers of my piece of wood, they're only connected by ligament. So let's say that I had a piece of wood like this. And if I want to push down with the bolt, like let's say my finger is a bolt here, if I want to push down, what can happen is basically I'm failing in shear the fibers, or the connection between the fibers actually. So if I push down like that, if the connections between the fibers are the weak point and I push only those straws down, then what happens is out the bottom, I'm basically pulling out a plug of wood. Right? And as I pull, that plug will move down and down and down, down and down and down like that. And so it comes out the bottom, the plug. And that's what we call row shear, because I'm basically taking out one row of bolts. So if those bolts are all aligned, they all together pull out a plug of wood. Like that. So I push this bolt down through the piece of wood, and only basically the strip of wood that is as wide as the bolt gets pushed out the bottom, and I have a failure in shear on both sides of that plug, which is exactly what I'm showing here. So I push the bolts down towards the end, and they push out plugs of wood, and I'll call those plugs shear plugs. So in order for this type of failure to occur, all of the rows of bolts have to pull out plugs together. So I have to find the strength of all of the plugs being pulled out. Why? Because if only one row failed, then the other row would still be holding that connection together, right? So that can't occur in a total failure. I mean, one of them might start to fail first, but then of course the other one is going to fail directly after that. So it's the total strength of all of the plugs together that will result in failure of the connection. So here I have my spacings like before. This is SR, which is the within row spacing in 08614, or we call that the parallel to grain spacing in 08619. And so in order for each of these plugs to fail, I have to fail along two lines. I need to fail this line here and this line here for the entire length of the piece of wood. So this is two failure planes. So we're going to see that come into the equation. And then the distance here, you know, my bolt used to be here before it moved. This is my loaded end distance in this case. We call that AL. Okay, now in practice, like we can have a lot of different, you know, my spacing, my row spacing and my loaded end distance can be different. Like each one could be different if I want. But we'll see in the equation, it takes a conservative approach. Basically, whichever spacing is less, the row spacing, the in row spacing, SR, SP, or the loaded end distance, whichever one is less, that's the one that you assume that they all have. So you assume that all of the different distances are the same. We're going to see that come into play. Okay, so this is what it looks like if I have failure in tension, so my plugs pull out the bottom, but it turns out that I can also get row shear failure in compression, and it would look like this. Okay, so let's say I have basically failure in compression now. So instead of pulling up and the shear plug going out, say I'm pushing down, okay? Now, it only makes sense really if I have multiple bolts here. Just one bolt doesn't really make sense because that's only embedment failure. But if I have multiple bolts, like I'm showing in the picture there, and the bolts are all pushing up because the member is in compression, and my bolt is restrained by something else, another piece of wood behind or a steel plate or something like that, then I can actually get row shear failure in the other direction as well, because I can still form those plugs in between. Now, where are the plugs going to go? Well, you know, obviously we're going to have some embedment failure of the top bolts so that the bolts will move up over here, right? So the bolts are moving up because of an embedment failure. And then the rest of the wood is failing as plugs, those orange kind of plugs of wood, which are just like chunks of wood being pushed up. And we calculate basically the exact same way. It's just that in this case, we're going to consider that ACRI, which is the critical length for the equation, which we're going to see in a minute. We haven't covered what that is yet. We're going to just set it to the row spacing, the in-row spacing, or the same as the parallel to grain spacing in 08619. And that's going to be this spacing here. So what we're basically assuming in that direction is that we have a plug over here that is the same length as the row spacing, that basically we're assuming that it fails as well into that piece of wood. But really it's kind of embedment failure that's happening at that. So when we're talking about row shear failure in compression, it's kind of an approximate approach, but we're supposed to check it anyways, using the same equation basically. So here's how we deal with that if we're loading it in the other direction. Okay, so that's fine. Okay, so now how do we go about calculating this? Let's look at the mechanics of what's happening with row shear. Okay, so let's say that we have our row shear condition happening here, and we already said that we have to fail 2 shear planes, one on either side, in order to pull out the plug, because the plug, which is the part in between, has 2 sides that are connected to the wood. So we have to fail this side and this side for the plug to be able to pull out. So this is the geometry. You know, the plug is about as wide as the bolt, something like that. Okay, and let's assume for now that we have the row spacing and the end spacing all the same, all equal to L. Okay, so how do we calculate the row shear strength per row? So I'm only looking at one pair of those red lines. Okay, so what is it going to look like, the strength? It's going to be equal to basically 2, because I have 2 shear planes, times A, which is a shear area. That's the area of the plane that needs to fail, times some unit shear strength F. So, right, so like this is just from basic mechanics approach. We have an area and we need a stress, like F is a strength in terms of stress, and then 2 shear planes. So that shear area is going to be basically the length times the thickness, right? The depth of that shear plane. So if I'm looking at this geometry specifically, it's going to be 2, right, times, and then what's the area? It's going to be 3L times T, which is the thickness of the member out of the plane, times some, we've called that before, FV. So is this a good calculation for the shear strength? Well, you know, it turns out that, you know, this 3 is going to be basically, we're going to call that NC, which is the number of bolts per row. So the number of bolts per row is the same as the number of spaces between bolts, right? I have 1, 2, 3, and that means I have space 1 here, space 2 here, and space 3 here. And L here is basically our length of each spacing. So that's going to be basically our row spacing, right? Our spacing of the bolts within the row. We're going to call that ACRI. T is our thickness. And here, it has been found that a good estimate of the strength here is going to be 0.6 times FV, which is based on test data. So we're going to find our shear strength, FV, which is the same strength that we used for longitudinal shear before, but based on test data, it's only 60% as strong when we're looking at the level of a connection, rather than at the level of a full member. So if I multiply all those things together, then I'm going to get something that looks like, right, I'm going to make my 3 NC, I'm going to make my L CRI, I'm going to make my FV 0.6 FV. So then if I have 2 times 0.6, I get 1.2. Then I'm going to have my NC. Then I'm going to have my ACRI. I'm going to have my T, and then I'm going to have my FV. Okay, where NC is number of fasteners per row, and ACRI is a critical length. So, like if this one here was different than this one here, then you'd say, okay, well, technically I should just add up all the actual lengths. But the standard takes a conservative approach. Whichever one of those individual lengths is smaller, it uses those for all of the different lengths. So for every single spacing between bolts, including the spacing between the bolt and the end, we use the same value, which is whatever is the minimum of all those. Okay, so that's what we might come up with if we started from a mechanics approximation, like a mechanics approach. How is it in 086? Okay, so in the standard, this is the equation that we get. You'll notice the parts that we just came up with, these and these, were from the equation above. And then in addition to that, we have KD, KSF, KSV, the service factor for shear, times KT. So you know how to find those from before. And then we have this extra factor, KLS, which we're going to talk about in a minute. So you can't really tell exactly what KLS means from the name, factor for member-loaded surfaces. We're going to look at that in a second. And then, of course, we need to formalize how we calculate this parameter ACRI. Okay, ACRI is the minimum of the loaded end distance, which is this distance here. That's our AL, if you recall, loaded end distance, and or our SR/SP, which is our parallel to grain distance, or our in-row spacing, depending on whether you're talking about 08614 or 08619. The parameter is the same, just has a different name. Okay, so it's basically the minimum of all of the spacings, basically. So that is a conservative approach because it then multiplies that by all the others. So you have basically no incentive to make AL any greater than SP, because if AL is greater than SP, then that extra length is not going to come into play at all in the row shear strength. Okay, so it's better to make them all basically the same. Or, I mean, you might have a geometric requirement for why you might make AL bigger, but it won't affect your strength if you do. Okay, so what about this factor for member-loaded surfaces, KLS? What is that? Okay, so here is a 3-member connection. This applies to 2-member connections as well, but it's only different for 3-member connections. So here's a 3-member connection with a bolt or a dowel. I've kind of drawn it as a dowel. Remember, a dowel is just a friction fit pin, basically, that acts the same way as a bolt, except it doesn't have a head and a nut. Okay, so when this bends, right, you can imagine, we're going to get some bolt bending shape. Okay, at the end of the bolt, we're basically not going to have that much load because the bolt is flexible. So when it's bending, at the end, I'm going to get less and less and less stress as I get toward the end of the bolt. So if I were to draw the stress profile in the wood caused by this bolt, okay, at the outside of the bolt, right at the end, I'm going to have basically 0 stress. Okay, and as I get closer to the center, I'm going to increase and increase my stress. So my stress is going to be largest at this point of shear, which makes sense. I mean, where I have my bolt and I'm shearing my bolt, okay, and if you do this with your fingers, you'll find, you know, that I'm going to have a lot of force right at this finger where I'm shearing, and basically not as much force on the outside. Okay, like stress-wise, not force. I'm going to have the most stress right at the interface, okay? And same thing on the other side for the outside bolt. It's going to look something like this. Okay, so this is my stress. In the middle, you know, I'm going to have a higher average stress, you know, in this case, because I have only one member in the middle and two on the outsides. So I'm going to have the same thing. I'm going to have more towards outside and less towards the middle, but it's going to be more uniform, because I'm loading the bolt kind of along its whole length here, and it doesn't have a free end. Okay, so this is going to be kind of what the bolt profile, stress profile is going to look like in the centerpiece. Okay, so on the outside, I have kind of a non-uniform distribution. Okay, so since I have this non-uniform distribution of stress, that means for the same total amount of force, I'm going to have a higher stress here than if I had a uniform distribution of stress, right? If I had a uniform distribution of stress, I would have something that looked like this. And if I added all that area up, I would get what the force is, right? But since my stress is not uniform, for the same amount of force, meaning kind of the same area under the curve, I have to have a higher actual value of stress over here, right? So my stress at that one point goes up. Okay, that means that basically I'm going to fail and crack earlier than if I had a uniform distribution of stress. So for that reason, we apply a strength reduction factor for this member in the connection of 0.65. And same thing over here, KLS equals 0.65 to account for this non-uniform distribution of stress. Now for the one in the middle, it is more or less approximately uniform, certainly by comparison. Okay, and since it's more or less uniform for the center member here, my KLS is going to be 1.0. So for 3-member connections, the one in the middle has a KLS of 1.0, and the ones on the outsides have a KLS of 0.65. And that's basically all you need to know. In a 2-member connection, both members are side members, so both members are going to have this kind of stress distribution. So since both members in a 2-member connection are side members and they're going to both have that kind of distribution, this non-uniform distribution of stress, then for both members in a 2-member connection, I'm going to use KLS equal to 0.65. Okay, so to sum up row shear, what I'm going to do is give basically a step-by-step method using the clauses from the standard to show you how to go through and do a full design. Okay, so when we talked about the yielding resistance, I made a point of talking about the fact that yielding resistance is one calculation for the entire connection. So if this is my connection, the whole connection, I have one yielding resistance that I calculate. Okay, all of the rest of the checks are not like that. So for all of the rest of the checks, I have to check for each side of the connection separately. Okay, so what do I mean by side? Okay, so here I have, for example, left side has just this connection, this member, and the right side has just this connection. Okay, so if I have 2 pieces of wood, and these are connected together like this, okay, I have one member on the left side and one member on the right side. So if I'm calculating row shear for this, and I have bolts connecting these members together. Then for the row shear, I need to calculate row shear for this member, okay, because I'm going to calculate what it takes to take the two, if I have two bolts here, what's it going to take to pull a plug out of the bottom of that? And then I'm going to repeat that process for this member because I could have two bolts pulled out the end as a plug. Okay, or I mean, we talked about the fact that we can calculate row shear as well for pushing on the member as well. So I get row shear if I compress, or I get row shear if I have tension. Okay, so I'm going to calculate it once for this member and once for this member. Why? Because these members could be different. They could be made of different materials. They could have different thicknesses. They could be different sizes. One is wood and one is steel. So if one of them is steel, I'm going to calculate row shear using S16, which we're obviously not going to do in this course. Okay, so each side of the connection is separate. Now, if I have three members, which I don't really have three pieces of wood here, but let's say that my book is one piece of wood or a piece of steel or something, and I have two pieces of wood on the outside. Okay, so here's my design manual. So now if I were to pull this connection, okay, apart like this, okay, so, and I've connected all three of these pieces together and I pull them apart like this, I'm going to have two members on this side of the connection. So these two together are taking that tension load on this side, and the book in the middle is taking all of that load by itself on the other side. Okay, so this side of the connection then has two members, and this side of the connection has one. And so I have to calculate row shear for basically each of these members, because again, they could be different. So this one could be one piece of wood, and this one could be a different piece of wood. So I'm going to calculate row shear for this one, row shear for this one, and then the total row shear resistance for this side of the connection then is going to be the sum of the row shear resistance for this one plus the row shear resistance for this one. On the other side of the connection, maybe it's my hand this time, it's a bit easier to hold. If my hand is in the middle here, then I'm going to calculate row shear resistance for this side separately. Okay, so then how am I going to know when the connection fails altogether? Either this one could fail, so this one could fail in row shear, or these two together have to fail at the same time, so the sum of these two. If either of those things happen, then the connection is going to fail in row shear, right? I mean, obviously my other option is that I could have a yielding failure, where I only have one yielding failure calculation for the whole connection, or I could fail in group tear out or net section, which we haven't talked about yet. Okay, so if we go back to the calc here, okay, so for the two-member connection, I have one on the left side and one on the right side. So I'm going to calculate my row shear for my left side. Then I'm going to repeat the entire process again and calculate row shear for the right side. And whichever one of those is less is going to be basically the row shear strength of the entire connection, right? For a three-member connection, which is the one that I was looking at with the book in between or my hand in between, then I have two members on my left side and only one member on the right side. So for the left side row shear resistance, I'm going to find the row shear for each of those members on the left and then add them together to get the total row shear resistance for the left side of the connection. Okay, if those two are the same members, then I can calculate row shear for one of them and then multiply it by 2, right? Because I'll have double the strength if I have double the members. Double the members and double the fun. Okay, so let's go through the actual step-by-step process of how to do this. So again, we have to calculate separately the connection on the left side and the connection on the right side. Okay, and this only applies to wood members, obviously. So this will only give me one or the other. Okay, so step 1. Okay, so for each side of the connection, okay, so all of this is just for one side of the connection. I have to go through each member on that side. So in a 2-member connection, I'm only going to do this once because I only have one member on that side. But in a 3-member connection, the one above, on the left side, I have 2 members. So I'm going to repeat step 1 for each of those members. Okay, so for each of those members, first thing I'm going to do is calculate the row shear resistance of each individual row. So for example, let's say that I have a piece of wood like this, and I have my bolts, Okay, then I'm going to have 2 rows for row shear, right? I'm going to have that one, and I'm going to have that one there. Okay, so this is going to give me row 1 and row 2. And so that's going to be PRI1 and PRI2. Okay, so going back to our equation for PRI, J here. Okay, so PRI, the I is the member number and the J is the row number. Okay, so PRIJ is for, member number I, row number 1, and row number 2. Okay, so that's how I calculate it. So I have the equation to calculate that. Okay, it's pretty straightforward. It's just based on shearing both sides of the plug to pull the plug out of the side. Okay, and I'm going to repeat it here. Now, in this case, for example, if I have one distance that's like this and another distance that is like this, this is the one that's going to be ACRI, right? It's going to be the shortest one that governs. Okay, we already talked about that. Okay, so then now that I have calculated the row shear resistance of each row, I'm going to find which one of those rows has the lowest row shear resistance. And I'm going to say that that one, whichever row has the lowest row shear resistance, I'm going to make that one equal to my PRIJ min. Okay, so I don't get any benefit in having one row that is like a lot longer and a lot stronger than the others, because basically whichever one has the lowest resistance is going to govern for the whole connection. Okay, so I'm going to assume that all the rows have the same strength, just like I'm assuming that all spacing between the bolts in a row is the same. That conservative part that we talked about, including the end distance, they're all the same. That's what PRIJ assumes. Likewise, I'm going to assume all the rows that pull out all have the same row shear strength. Once I have that minimum, now I'm going to find the total row shear strength of that one member. Okay, and I have my phi W, which is a reduction factor. I take my IJ min, which is the minimum of all the rows, and then I multiply that by the number of rows. So that's how I get basically, I use the minimum row shear for all of the rows. And I use a 0.7 reduction factor because it's a brittle failure mode. Okay, so once I do that, I'm going to repeat that for all members, right? Repeat. Okay, for all members on that side. So I'm only looking at, if I have a 2-member connection, there's only going to be 1 member that I do here. If I have a 3-member connection, if I'm on the left side there, I'm going to have 2 members to do this number 1 calculation for. And if I'm on the right side, I only have 1 member to do that calculation for. Okay, so then once I have the resistance for each member, they could be the same. If I have 2 of the same member, then, PRI is going to be the same for member 1 as it is for member 2. Okay, so then in the standard, PR stands for, P is a compression tension resistance, R is for row shear, small r means resistance, T here means total, is the sum of all the PR, R for resistance, I for which member. Member 1, I equals 1, or member 2, I equals 2. So if I have 2 members, I just add those strengths together and I get my total row shear resistance for that side of the equation, either the left side or the right side. And if I have wood members on both sides of the connection, then I'm going to have to repeat this entire process again for that side of the connection. And that's it. Once I have PRRT, that's my row shear strength for that side. Okay, so row shear is quite complicated, so I'm going to put a cut here, and in the next video we're going to continue with the non-ductile failure modes and talk about group tear-out failure.